Good morning, students. I hope you all are well. Yesterday, we defined the word vector space with the help of basic concepts. Today, we will consider some examples on this and we see how to prove a given set with internal composition and external composition of vector space. Okay, so let's see. V is a vector space over the field F. This is denoted as this one. If this is given, it means here V is a vector space this is a set with two binary compositions. V is a vector space over the field F. This is denoted by this particular symbol. What is V here? This is a set equipped with two binary compositions denoted by this symbol and this symbol. What is this? Addition of vectors. This one is scalar multiplication. Addition of vector means V cross V to V such that the image of this is alpha plus beta. Scalar multiplication, composition, this is external F cross V to V such that this was explained yesterday very well. If you are not able to understand again, then you go through the previous videos again and again and again. There is no shortcut. Several times I told you. So here the sentence is V is a vector space over the field F. This is denoted as this one. This is a set that is non-empty. It must be non-empty set. Equipped with two binary compositions. One is denoted by this symbol. Remember, this is not ordinary plus. This is multiplication. It is not ordinary multiplication. Ordinary addition, we use this symbol. Ordinary multiplication, we use this symbol. But while doing questions and all that, instead of this, we write simply A alpha. And here it is, we write simply alpha plus beta. Okay, so V is a vector space over the field F. It means we have these things. Set equipped with two binary compositions. One composition is this, other composition is this one. This is internal composition, means V cross V2. V, this is addition. So elements of V cross V will be in the form of pair. So image of alpha comma beta will be sum of these two elements. It is alpha plus beta. In the similar manner, scalar multiplication means one member is scalar, that is a number, other member is vector, so it is from F cross V to V. So members in this set, that means the domain set, will find A comma alpha. That is the scalar multiplication. So the sign multiplication is used here, or simply we say A will be denoted by A alpha. This one. A is a scalar, alpha is a vector. So the sign between this one is not ordinary multiplication. Here this is scalar multiplication. ये आपको ध्यान रखना है. This set V is a vector space if this composition satisfies some properties. In the similar manner, this composition will satisfy some properties. What are those properties? We have done. The first one is an abelian group. First one is this. This must be a abelian group with respect to this composition. Abelian group means 5 properties: closure, associativity, commutativity, existence of identity, and existence of inverse. This one. So this abelian group means 5. Second one, combined properties of these two. First one, closure property. Second, distributive. Third is also distributive. Fourth, associativity. And fifth one is the unit element with respect to F. So this we have done. Do not get any confusion. The main thing is don't think that there will be so many properties. Actually, the key point is we simply want to add vectors and multiply them by scalars without too many difficulties. Okay, so this you have done, and you remember the elements of set V are called vectors. Here the vector doesn't mean the vector quantity that is defined in vector algebra and physics. Okay, so here vector may be the matrix, vector may be the polynomial, vector may be the function or any other thing also. So now you can say here simply we want how to add two vectors and how to multiply that vector by a number, that is by constant. This we have done in previous classes, that is in class 12, how to do that. So you just remember what is going on in vector space. It is simply to add matrix and to multiply a matrix by a number, nothing more than it. To add matrix, that means to add two vectors and the properties of this addition. Similarly, to multiply the matrix, that means to multiply a vector by a number, so it is scalar multiplication and some common properties between all the things. Okay, so let us see. As I explained yesterday, F, that is filled here. That means it is a triple. Non-empty set. Internal binary composition, F cross F to F. Addition of scalars and dot, again internal. Here it is A comma B, that is A plus B. This one is multiplication. That means A comma B, the image is A dot B. Simply say this way. Then this is commutative group. This is also commutative group, and the combined properties of these two, that means the distributive property, that is A dot B plus C, A dot B plus A dot C, left as well as right. This includes 5 properties, this also 5 properties, and distributive. So 5 plus 5 plus 1, that is 11 properties. Do not think about that we have to learn 11 properties. You think that how to play with real numbers in lower classes. Add, multiply, divide, subtract, all that type of situation. Distributive, associativity, commutativity. So in all, this has 11 properties. So this is a field, means it is a triple. Vector space, it is also a triple with 2 binary compositions. Here this is also triple with 2 binary composition, ordinary addition and ordinary multiplication. Ordinary addition means addition of numbers. In vector space, addition of vectors. Vector, maybe matrices, maybe to polynomials, maybe to functions, and all that. Okay, but now suppose F is Q, then this is field of rational numbers. You have to remember all the basics. Okay, so if f is q, then it is known as field of rational numbers. If suppose it is r, then it is field of real numbers. Suppose it is c, then it is field of complex numbers. Suppose I say it is field of the numbers of type a plus b root 2, where a, b belong to q. A and b are numbers. Like this. Here, this is rational number, this is also rational number. So, this type of number is the member of this particular set. It is denoted like this. Okay, so if any specific field is not given, again I am telling you, if any specific field is not given, then you consider the given field is the field of real numbers. So if I say V be a vector space over the field F, means here F is the set of real numbers. Okay, so it is this type of situation. Z set of integers, that is what is this? This is the field, this is also the field, this is the field, this is also the field. This is given in abstract algebra. Z, this is the set of integers. If I consider a triple, then how to check is it a field or not? If it is a field, then you see the 11 properties we have. The best way is, whenever you have to check, the best way is, first you verify the closure property of these two compositions. Suppose while simplifying this one, then we have to prove this is commutative group with respect to addition. Then closure property, associativity, identity, inverse. Suppose it is satisfied. Then I say Z is an abelian group with respect to this. Dot closure property, multiplication. Suppose it fails. If one of the properties failed, then it is not a field. Out of 11 property, is one of the properties failed, then it is not a field. So suppose it is failed in closure property of multiplication, then that is time consuming process to check that this is an abelian group. So it is better to check closure property of this and this one first. Okay, now we know that sum of two integers is an integer, so addition is closed. Integers follow the associativity law and commutativity with respect to the plus sign. 0 is the identity element, and every member of Z has its additive inverse. Additive inverse means the additive inverse of 2 is minus 2, and minus 2 is the member of that. But if I consider this ordinary multiplication, then multiplication of two integers is again an integer. Which property holds? That is the closed property. Multiplication is commutative, multiplication is associative, and 1, that is the integer, is the identity element. If you multiply every integer by 1, the answer is the integer itself. So 1 is the identity. Now the inverse. The inverse of 2, that means the inverse of multiplicative 2, that is non-zero element, is 1 by 2. And 1 by 2 is not the integer. So Z is not a field. Okay? So Q, this is a field. R, this is a field. C, complex numbers field. This is also field. You can prove this one. But Z with these two compositions is not a field because multiplicative inverse of integer does not exist in the set of integers. Inverse multiplicative inverse of 2 is 1 by 2, but 1 by 2 itself is not the member of Z, so it is not a field. Okay, so it is that type of situation. Check whether see, check whether this algebraic structure is a vector space or not. These things you are given. This is the given part. Always remember, we will solve these two questions also. That's why they are written here. Whenever we have to verify the given set is a vector space or not, then first you have to identify the set which is given. First point, which set is given. First, identify the set. Second, the nature of the elements of that set. Third, the composition defined, means binary composition defined. And fourth, the rule of the composition. Here we see Z, set of integers, Q, set of rational numbers. Q will behave like field, so we have to check the set of integers over the field Q is a vector space or not. With respect to ordinary addition and ordinary multiplication defined by this. So here Z is the given set. These two compositions are defined. Ordinary plus means the image of this one is given by this rule. Image of this one is given by this rule. Come to this question. Check whether the set V is a set of points in 3D. This is the way to read the mathematics. पढ़ना आना चाहिए, मैथ्स को किस तरह से पढ़ते हैं. V is a set of triplets, means this is a point. X is from R, Y is from R, and Z is from R. So it is R cross R cross R. If you write X comma Y just like A comma P, then it is from this one. First component is from first set and second is from second. So here it is from this one and here it is from this one. Remember, Q and Z both are the set of numbers specifically. Here it is also this. So here it is R cross R cross R, so it is R cubed. Means the point in the space, any point you consider in the space. So this V is a set of points in 3D, nothing more than it. But satisfying this rule, 2x plus 3y square minus 4z square equals 0. So whenever you consider the element, it must be satisfied by this rule. Okay? Now come to this one. This we have to prove a vector space. As I told, the first you verify the closure property, that is the closure property of addition as well as closure property of scalar multiplication. Here scalar multiplication coincides with the multiplication. अदिश गुणनफल जो है वो सिंपली गुणनफल की तरह ही दिखेगा. कारण यह है कि दोनों सेट नंबर्स है, इसमें भी नंबर्स है और इसमें भी नंबर्स है. ये मैट्रिक्स का सेट नहीं है, ध्यान रखना है. ये वाला सेट जो दे रखा है उसके एलिमेंट को हम वेक्टर कहते हैं और यहाँ वेक्टर जो है वो इंटीजर है. So here members of Z are vectors, means 0 is a vector, 1 is a vector, minus 1 is a vector, 2 is a vector, minus 2 is a vector. So every integer is known as vector in this. Q set of rational numbers, उसमें कोई doubt नहीं है. So here this is the set of numbers, this is the set of numbers. So the plus with circle coincides with the ordinary addition. And scalar multiplication is the ordinary multiplication. Okay. Now we come to this one. Sum of two integers is always an integer. And you remember this belongs to this one. Here it is. It must be in this. It must be in this one. Now if I consider from Q, Sorry. Two by 3 is a rational number. Minus 5 is an integer. So we have this pair means operation, the multiplication, is it an integer? No. Therefore, the closure property of scalar multiplication is failed. Multiplication is failed. Therefore, this हमने इसको अबेलियन ग्रुप प्रूव नहीं किया है। वेक्टर स्पेस के लिए जरूरी है अबेलियन होना चाहिए, नहीं किया। क्लोजर प्रॉपर्टी देखी, हमने इसके लिए क्लोजर प्रॉपर्टी देखा एंड दिस प्रॉपर्टी इज फेल्ड, सो इट इज नॉट अ वेक्टर स्पेस। ओके, now we come to the first question. Check whether the set V is given this, is a vector space or not. What is the triple here? V. Addition and multiplication. Addition means this one and multiplication this one. Over the filled R. Remember. Check whether the set this is a vector space or not. Over the filled R. Field is not specified, it is not given. Assume that this is the set of real numbers. That is this. Okay, so let's say let's consider any two members. That is alpha comma beta. Closure property. Listen. For all alpha beta belongs to V implies alpha plus beta belongs to V. Suppose this and this be the members of V. Why is it like this? You see the nature of the elements. A point in 3D. So this is a point in 3D, you can say. It is not necessary to consider this one. I took the y coordinate 0. So these 2 points are in zx plane. यदि मैं ज्योमेट्री की बात करता हूं तो जेड एक्सप्लेन में दोनों पॉइंट है। यदि मैंने ये दोनों पॉइंट्स लिए हैं तो क्या ये इसको सेटिस्फाई करता है, ये चेक करना है, तभी ये इसका मेंबर होगा, नहीं तो नहीं होगा। यदि मैं इसको हटा दूं यहां से, इसको बाय द वे इस पूरी इस कंडीशन को हटा दूं, इसका मतलब V जो है वो कंप्लीट 3D के पॉइंट्स का हो जाएगा। एक्स वाई जेड बिलोंग्स टू आर क्यूब्ड means every point in 3-dimensional will be the member of V if this condition is not given. Here the condition is specified, means you consider those points in 3D which are satisfied by this relation. So you just check. 2 into 2 is 4, this part is 0, z is 1, so this 4 minus 4 is 0, so this point is a member of V. Next one, it is 8 to the 16, this is 0 and minus 16, this is also 0. So this is alpha and this is beta. Alpha and beta both are the members of V. Now alpha plus beta must be the members. Okay, so now alpha plus beta equals 201 802. So, and always remember, two ordered pairs will be added. And how to add? First component is added to first, second is added to second. In the similar way, triplet, first to first, second to second, third to third. Similarly in n dimension, that is called n tuple. But this time we are doing triplet here. So it is 2 plus 8, that is 10, 0 plus 0, that is 0, and 1 plus 2, that is 3. What's the condition? If alpha beta be the members of V, then alpha plus beta must be the member of V. Now we check. We found the points. If it is this, it must be satisfied by this relationship. If it is satisfied by this relationship, then this will be the member of this. Only one counter example is sufficient not to prove this. Okay, so say verification. This is 10 times 2 plus 3 times 0 minus 4 times 3 square. So this is 20 minus 36 and this is minus 16. And this is not equal to 0. Therefore, 10, 0, 3 does not belong to V. So, closure property does not hold. Closure property is failed. Therefore, this is not a vector space. Therefore, V is not a vector space. Closure property. Which one? Addition. Closure property is failed. So this is not a vector space. Similarly, you try this question. This is for homework. You just find the counter example in such a way that this is not a vector space. If it is a vector space, then it's okay. The similar, again, you people are given this. Here it is 0. Sorry. just like this. This is a point in 3D, but it is satisfied by this relationship. So if you find any counterexample in such a way that any one of the properties failed, then it is not a vector space, otherwise it is a vector space. So this is the way to consider a particular example and how to verify this one. We will consider some more examples on vector space in the next class or in next video. So you try this particular question given to you. If you find the answer, whatever you write the comments in the comment box. If you have any difficulty, you also comment that particular comment box. Thank you very much. Jai Hind.